Okay, so on page 7 of your in-class problems, we have the second problem where we're identifying the oxidation numbers of all of the elements in this reaction. Just a reminder, oxidation is what? When we're losing electrons. And what happens to the oxidation number? It goes up. And then what's the other part of redox? Reduction. What's happening with electrons when we are being reduced? We're gaining electrons. And the oxidation number is doing what? Going down. Okay? So, to review this, oxygen, when it's in a compound, is typically what? -2, right? So like here, this would be -2. Here, it'd be -2. And here, it'd be -2. The exceptions to that are when it's a peroxide, which we're not really going to deal with too much, or when it's with fluorine, which isn't the case here. Okay? What about this oxygen? It's 0 because that's by itself. It's elemental. Even though it's diatomic, it's still alone. It's only oxygen there, so it's 0. Okay? Hydrogen is typically what? +1. Unless it's with a metal, in that case, it's -1. But we have no metals in this reaction, so every single hydrogen has what oxidation state here? +1. And now for my carbons, in CO2, what's the overall charge on CO2? 0, because it's electrically neutral. So in order for that to be 0, and for oxygen to be -2, what does that carbon have to be? +4. Algebra, right? And then let's write out the work for this other carbon, just because it's a little more complex there. So C2H5OH, right? What's the overall charge there? 0. We have 2 carbons. How many hydrogens do we have? 6. 5 plus the 1. We can just combine that to make 6. Plus the oxygen all adds up to 0. Okay? Now let's fill in the oxidation numbers that we know. We don't know carbon, that's what we're solving for. Each hydrogen is +1, and oxygen is -2. So go ahead and do that algebra, middle school algebra right there, to figure out that carbon is -2 there. So this carbon is -2. So now, the substance that is being oxidized is the one whose oxidation number goes up from left to right, which would be what? Carbon, because it went from -2 to +4. And what's the substance or the element that's being reduced? Oxygen, because here it's going from 0 down to -2. Yes, there's still an oxygen that's going from -2 to -2 that isn't changing, but we do have atoms of oxygen that are being reduced. Okay? Recall all that? Cool? All right. So on page 8 of your in-class problems, we're going to be going through how to balance redox reactions. So in your guided notes, if you want to turn to page 14, at the bottom of that page, we have the steps for balancing redox reactions. And I will briefly write out those steps when we do the problem for anybody who doesn't have their guided notes with them today. All right. So in a redox reaction, I think I said this last class, but just a reminder. So in all reactions, what's happening is the atoms are being rearranged. You might have some atoms that are bonded together on the left side, and then they're bonded with something different on the right side. Okay? In a redox reaction, we not only have the rearrangement of the atoms, but we also have a transfer of electrons. the element that is being oxidized, it's losing electrons, and then the element that's being reduced is gaining electrons. The element being oxidized gives the electrons to the element being reduced. Okay, so it's a complete transfer of those electrons. That's why you can't have one thing without the other. You cannot have oxidation without reduction, or vice versa. Okay? The electrons have to go somewhere, they have to come from somewhere. They don't just go into nothing or disappear or appear. Okay? So, when we balance redox, we're not only balancing the elements, but we're also balancing the charge. Okay? So there are several steps to doing this. I love balancing redox reactions. Okay? And your homework for tonight is, well, okay, let's be honest. Your homework for Monday night is all just balancing redox and redox type problems. Okay? So our first step, the fact that it's in acidic is going to come into play in a little bit because redox reactions typically occur in acidic or basic conditions. So we need to know if it's in acidic or in basic solution. Okay. So first thing we're going to do is divide our reaction into our two half reactions. So we're going to split this into our two half reactions. So I'll show you with this first one. So our two half reactions are going to be S2 minus going to S8 and NO3 minus going to NO2. I'm leaving off the states of matter for right now because this is all like that work in between that you will need to show on like a test, but it's all the work in between. I'll put back in the states of matter at the end. Okay. So that's our first step. I've split it into our two half reactions. Step 2 is to balance everything that isn't oxygen or hydrogen. Just normal balancing, adding coefficients. That's supposed to say O and H, not OH. O and H. Balance all but oxygen and hydrogen. Oh my gosh. I just realized I wrote the 8 up here. It's supposed to be a subscript. I don't know what I'm doing. So happens when I talk and write at the same time. It was S sub 8, not a exponent 8. Sorry about that. All right, so in our first half reaction, we don't have any oxygen or hydrogen. We only have sulfur. So how am I going to balance the sulfur? Yep, I'm going to put an 8 coefficient in front of S2 minus. Just normal balancing. For my second half reaction, are my nitrogens balanced? Yep, so we don't need to do anything more for my second half reaction right now. So I'm done with step 2. Step 3 is to balance the oxygens with waters. Okay? We're going to balance the oxygens with waters. So the way we're going to do that is we're going to add the appropriate number to make things balanced of water molecules to the opposite side of that half reaction. Okay? So in my first half reaction, I have no oxygen, so I don't need to do anything more with that one for now. My second half reaction, I have 3 oxygens on the left and 2 on the right. So I'm going to add 1 water molecule to the right so that it gives me a total of 3 oxygens on the right, balancing out the 3 on the left. Step 4. Balance hydrogen with H plus ions. So same type of thing we did with the waters. We're going to add hydrogen ions to the opposite side to make them balance out. Okay? So in my first half reaction, I have no hydrogen. I don't need to do anything with it. My second half reaction, since I added those waters, I have 2 hydrogen atoms on the right. I need to balance that by adding 2 H plus ions to the left. So far, so good? Okay, it's very systematic, step by step by step. Step 5 is we want to now deal with the charge. So we're going to balance the charge with electrons. Okay, so pop quiz. What charge do electrons have? Negative. Each electron is a -1 charge. So when I figure out the overall charge of each side of each half reaction, I'm going to be adding electrons to the more positive side because you'll be bringing down that overall charge to meet the other one. Okay, so looking at this first half reaction, what is the overall charge on the left? Negative what? Negative 16, because I have 8 S2 minuses, and 8 times -2 is negative 16. So I have a negative 16 charge on the left. And what is my overall charge on the right? 0. So which side is more positive? The right. So I need to add my electrons to the right. How many electrons am I going to add? 16 of them. Tripping over things. Okay. And now for my second half reaction, what's the overall charge on the left? +1, because I have a +2 here and a -1. 2 plus -1 is +1. And what's the overall charge on the right? 0. So which side is more positive? The left. So how many electrons am I going to add to the left? 1. What do you notice about where we added electrons? We added them to opposite sides for each half reaction. That is how it will always be. Because, like I said before, whatever is losing electrons, like our sulfur here, has to be gained by the other half reaction. That is a good check. When you get to this point, if you have electrons being added to the same side of both half reaction, you've done something wrong. Okay? Because that means that both of them are being oxidized or both of them are being reduced, and that doesn't happen. Okay? So it's a good check along the way. Now, our next step is to make the electrons equal. Okay? The electrons that are being lost by sulfur have to be the same ones being gained by the other half reaction. So we have to multiply the half reactions so that the electrons are equal. So multiply to make the electrons equal. All right? And when we multiply, we're going to multiply the entire half reaction. Okay, because whatever you do to one side of the reaction, you have to do to the other. So we don't need to worry about the first half reaction. We can multiply this second half reaction, the whole thing, by 16, which means every single coefficient in that second half reaction is going to get multiplied by 16. So instead of 1 electron, it's going to be 16. Instead of 2 H pluses, it's going to be 32. And then 16 here, 16 here, 16 here. Yes. We're about to do that. So you don't have to here. You can just cross through and change the coefficients if you wanted to. Okay? Just to save yourself time and space. Space, time, continuum. Okay. Never mind. All right. And then our final step for acidic conditions is to recombine and cancel out like terms. So what that means is I'm going to add my two half reactions back together, because remember I originally split them at the beginning, and I'm recombining them. Everything that's on the left side of both half reactions will become the full left side for the full reaction, and then everything on the right will become the full right side. Okay, and then we'll talk about canceling things. So let me just write down everything that's on the left side of these arrows. So we have, that's supposed to be an 8. I don't know what I'm doing. 8 S2 minus plus, that's the only thing on the left side of this first half reaction. Then everything here, 16E, 32H plus, 16NO3 minus, and then everything on the right, S8, 16E, 16NO2, and 16H2O. But now we're going to cancel things, right? Cancel like terms. So just like with our net ionic equations, those spectator ions, or the things that are the same on both sides, cancel out. For example, our 16 electrons. We have 16 electrons on the left, we have 16 electrons on the right. So our net is nothing, right? Both of those cancel out. And that's why we have to multiply them to make them equal, is so that they cancel at the end. Your final equation, when a redox reaction is balanced, will never have electrons shown. Okay? So does anything else cancel out? Nope, not for this one. So now our final answer, and I'm going to put states matter back in, is 8s2 minus aqueous plus 32H plus aqueous plus 16NO3 minus aqueous goes to S8, which is a solid, if you look back up at the beginning of the problem, plus 16NO2 gas. Give myself some more room here. Plus 16H2O. That's supposed to be an L, liquid. Okay, so that is our final answer. Okay. So you can look at this. You can check to see, are all of your elements balanced? They should be. You should have 8 sulfurs on both sides. We do. You should have 32 H's on both sides. We do. You should have 16 nitrogens. We do. What's 16 times 3? 48 oxygens, which we do. Okay? Not only should all of the atoms be balanced on both sides, but so should the overall charges. And that's why we had to do the electrons. Okay? So we have an overall -2, but plus 30, sorry, -8, -16, plus 32, so an overall plus 32 here, or plus 16, and -16, 0. It does work out. I know I went through that really quick, but it does. Overall, we have a 0 because it's -16 plus 32, that's plus 16, and then cancels out with the -16 here, equals the overall 0 here. Okay, so you can always go back and check. Now notice, we have H plus here. What were our conditions? Acidic. And H plus is an acid. Okay? Cool. What do you notice about this one? It's basic. It is basic. It's in basic conditions. But we're actually, the steps, there's a couple different ways you can balance things in basic. I find the easiest is to balance it as if it were acidic, and then we'll deal with the fact that it's basic at the end. Okay? So what I want you to do is take a few minutes to balance this reaction as if it were basic, or sorry, as if it were acidic, and then we'll come back together and deal with the fact that it is basic. All right, so I'm just going to quickly go through this when it's being balanced. So our two half reactions would be MnO4 minus going to MnO2, and then I minus going to IO3 minus. We don't need everything except for oxygen and hydrogen are already balanced, so we don't have to do any extra coefficients right now. So dealing with the oxygens, we need 2 waters over here and 3 waters here. And then we need 4 hydrogen ions here and 6 here. So far, so good. Hopefully. All right. And now the charges. we have an overall +3 for this half reaction and a 0 on this side. So we need 3 electrons here to balance out the +3. That means since we added electrons to the left for the first half reaction, we should be adding it to the right for the second half. And that is true because we have an overall +5 on the right and -1 on the left. So we're going to be adding 6 electrons to the right to bring it down to -1. 6. Because we have -1 on the other side. Yeah, it's not always 0. Okay. And that means that in order to balance that out, we need to multiply this first half reaction by what? 2. You need to multiply it by 2. So all of these get multiplied by 2. And now we're going to combine. What do we know is going to cancel? The electrons. Let's go ahead and cancel those. So when we recombine these, we get 8H plus 2MnO4 minus plus 3H2O plus I minus going to 2MnO2 plus 4H2O plus IO3 minus plus 6H plus. Ugh, it's a lot. How rude. Interrupting me while I'm teaching. All right, so now, what do you notice here and here? What do you notice there and there? What? Okay, or the fact that there's H plus on both sides. That's what I'm getting at. Okay, so we're putting in 8 H pluses and we're getting out 6 H pluses, which means what's our net? 2 in, right? So this cancels out to be 2 H pluses going in. Just like with net ionic equations, the only difference here is we didn't have the exact same number on both sides. So it doesn't completely cancel, it just reduces down. Same thing with our waters. We have 3 going in and 4 coming out. So what's our net? 1 out, right? So the 3H2O cancels, and that reduces down to just 1. Okay. All right, so now we're going to deal with the fact that it is basic, okay? So once you have it balanced as if it were acidic, I'm not going to rewrite for right now just because we're about to do something more to it and then rewrite it eventually. So the fact that it's basic. If acidic has H+, what does basic have? OH minus, okay? So we need to add as many hydroxides as we have hydrogens, but we have to add it to both sides of the equation. Whatever you do to one side, you have to do it to the other. So add hydroxides to neutralize the H pluses, okay? So how many H pluses do I have? 2. So I'm going to add how many hydroxides? 2. So I'm going to add 2 hydroxides to both sides of the equation. Okay. Second pop quiz. H plus OH minus is what? H2O. So what do our 2 H plus and 2 OH minus become? 2 H2O. Which now we have 2 H2O in and 1 out. So 2 in, 1 out. What's our net? 1 in. So this H2O completely cancels, and this reduces down to 1 because this became 2H2O, cancels down. Yeah. So now we're ready to rewrite it. We're done canceling things. Now we're going to rewrite. So we have 1 H2O, which is liquid, plus 2MnO4 minus plus, I know I'm blocking people. I will move it out of the way. Oh, that's aqueous, going to 2MnO2, which is a solid based off of the original problem, plus IO3 minus, which is aqueous, plus 2OH minus, which is aqueous. Yep, and you can go through and check to make sure everything balances properly. We're not going to go through that with this one. Okay? All right, so now we're going to do the last problem in the packet that I want to do today. This last problem, number 19, I love this problem. I love this problem. Whatever. This problem. I love this problem. I love this problem. I don't know how I can make it any plainer. It's on the test. Okay, so first thing we need to do, we need to balance it. We need to balance this equation. Okay? In order to balance it, do you want to sit back there just so you're not like, yeah. All right, so we need to balance this equation. What type of equation is this? Redox. Okay, so we're going to have to go through those steps. Now, there's a few things. It kind of tells you already that you're going to end with H plus on the left and H2O on the right. Ignore those for right now. Your two half reactions, the one will be the dichromate going to the chromium 3 plus ion, and your other one's going to be the iron 2 going to the iron 3. So separate this out into your two half reactions, and then go through the balancing again, okay? And I will pause this to give you guys a few minutes to balance this. This one's a little bit simpler than the last one, but take a few minutes to balance this. All right, so now that you've had a chance to balance this, our two half reactions are the dichromate going to chromium 3 plus and Fe2 plus going to Fe3 plus. All right, so our first half reaction, balance everything but oxygen and hydrogen. Okay, good, because that was a mistake yesterday in third block, and it therefore affected everything else. Okay, I'm just going to do each half reaction alone and then combine them. So to finish balancing this first half reaction, we need 7 water molecules on the right and then 14 hydrogens on the left. Okay. Overall charge on the left right now is plus 12. And on the right is plus 6. So that means I need 6 electrons on the left. So now my first half reaction is done. Second half reaction, iron's already balanced. There's no oxygen or hydrogen. The only thing I need to do is add an electron to the right. Isn't that nice? What am I going to multiply that second half reaction by? 6. And now I'm going to recombine. What's going to cancel? The electrons. Does anything else cancel? Nope. So 14H plus Cr2O72 minus plus 6Fe2 plus goes to 2Cr3 plus 7H2O plus 6Fe3 plus. Notice how we have H plus on the left. The problem originally was telling us that we were going to have H plus on the left. And we have H2 on the right, which the problem told us that. Okay, that was kind of like a hint. And, well, because this is unbalanced, so it's not really different quantities. It's just this was unbalanced, and now we've balanced it. Okay? Yes. What's 14 times 1? 14. What is 1 times negative 2? What is 14 plus negative 2? How about plus 12? So we have an overall plus 12 here. And then 2 times plus 3? Plus 6, which is why we got 6 electrons. Okay? Yeah, if you forgot to put a 2 in front of the chromium, your electrons would have been off, which then would have caused, you would have gotten 9, I think. You would have to multiply this by or something like that. Okay? So that was the balancing. Now, the math. Don't worry, since I've run out of room, I duplicated this page already, and I have another page. You should still have plenty of space on your packet. I'm just going to add in those coefficients that we figured out. This one was 1, this one was 6, this was 14, 2, 6, and 7. Okay. So, a solution of dichromate is prepared by dissolving 6.425 grams of potassium dichromate in 800 milliliters of water. So here's my beaker, my stock solution. Okay. In that, I dissolved 6.425 grams of potassium dichromate to make a total of 800 milliliters of that solution. And then I put that solution into a burette, which I then used to titrate. I'm getting there. Don't interrupt me, please. Which I then used to titrate a solution of iron 2 ions of unknown concentration, and that had a total volume of 250 milliliters. And it required 21.35 milliliters of my stock solution in order to do that. So the first thing I have to do is figure out the concentration of my stock based off of this. Now, what happened to the potassium? Well, potassium has to be present for the solid because it's there. In solid form, it's there. Once you dissolve potassium dichromate, what does it do in solution? What's that D word? Dissociate. So it dissociates into 2K plus and Cr2O72 minus. If it doesn't participate in the reaction, what is it called? A spectator. K plus was a spectator ion. Typically, those alkali metals are going to be spectators. They're not going to participate in the reaction. Okay, so that's where the potassium went. That's why here in our balanced redox reaction, which is always going to be a net ionic equation, the potassium's not there. It's still there in the solid form, but it's not there in solution, or it's not important in the solution. Okay? All right, so go ahead and we need to figure out the concentration of our dichromate in that solution by converting the 6.425 grams of potassium dichromate to what? Moles. For the sake of time, I'm just going to give you that molar mass. It is 294.2. So when you divide that, you should get 0.02184 moles of potassium dichromate. Now to find the concentration of that potassium dichromate solution, what do? Divide it by the volume of the solution that I made. How much of this solution did I make? 0.8 liters. Good. Because it's 800 milliliters. So 0.02184 divided by 0.8 will give us the concentration of our potassium dichromate, which you should get 0.02730. But I need to know the concentration of my dichromate ion. So let's look back at our dissociation equation. When we dissociated that, how many dichromates does it make in solution? 1, because the coefficient in front of this is 1. So we're going to multiply this concentration by 1, because there's only one dichromate. If I was asking for potassium, I would multiply it by 2. But because I'm asking for dichromate, it's the same thing. So that is the molarity of the dichromate. That's a Cr2O7. It's the same molarity. Okay? Now, that concentration is what we had in our stock solution. It's what we put in our burette. We needed 21.35 milliliters of that to completely neutralize the iron 2 ions. So this is just stoichiometry. This is what we were doing last class. Okay? So we're going to take the 21.35 milliliters, put it back into liters. So 0.02135. Is it 35 or 53? It is 35. Okay. Liters. Multiply that by the molarity, which we just solved for. And this is of my dichromate. And then multiply by the molar ratio to convert to moles of Fe2+. So mole dichromate, mole Fe2+. What is that molar ratio? Where can we find it? The balanced equation was the whole reason we needed to balance the redox reaction. It's just like any other Stoich problem. It's just longer because you had to balance redox versus just balancing a normal equation. Okay? So what is our mole ratio? 6/1. Okay? And just like with other free response questions, if this was a multiple part problem, the first part would be balance the equation. And then do the math. If you balanced it wrong, but did the math right with the wrong numbers, or like did the process right, you would get the points for the stoichiometry. You would lose points on the balancing. Okay? And that's how it's always been. So when you do that math, you'll get the moles of Fe2+ that had to be present in this solution. And then we can divide it by the volume to get the concentration. So the moles of Fe2+, when you do that math, you should get 0.003497. Is that right? Mole Fe2+. And now we're going to divide that by what? 0.2500 liters, that volume that we used, which is 0.01399. Okay, so it's a little bit of everything for that problem. What does it say right at the beginning of this problem? At the very, very top, in bold. If you can do this problem, you can do it all, because it's like everything from this unit. Okay?